Hey, everybody. Welcome back to EarthSky. Good morning, good evening, good afternoon, wherever you are on the big planet. And today we are joined by Rob Lillis. Rob is the Associate Director of Planetary Science at the University of California, Berkeley Space Sciences Laboratory. There's a mouthful. He's a space physicist and a geophysicist, and he specializes in Mars' atmosphere, its unique magnetosphere, and its crustal magnetism. How's that? Anyway, he is the principal investigator for Escapade, which is the Escape and Plasma Acceleration and Dynamics Explorer mission. And they're going to send a pair of CubeSats. These are tiny little sats all the way to Mars, and they're doing it on a shoestring. This is the economy class flight to Mars. And so anyway, this is not your first rodeo on Mars, is it, Rob?
No, I am maybe somewhat unusual in terms of planetary scientist that I've spent 90 to 95% of my career in just one planet with Mars. And this is my fourth Mars mission. I was a grad student during the second half of the Mars Global Surveyor mission, and I did my PhD on some of the data from that mission. Then I also worked, and I'm still working on the Maven mission. That's Mars Atmosphere and Volatile Evolution mission, another NASA mission to study the upper atmosphere of Mars and atmospheric escape. I was also lucky enough to work on the Emirates Mars mission. So this is a partnership between Berkeley, the University of Colorado, Arizona State University, and the United Arab Emirates Space Agency. And we've been working closely with them on what is essentially the first Martian weather satellite. It's in a high orbit, just like Earth geostationary weather sats. And so it's looking at Mars from a very different perspective than the much lower orbits that most of the other missions have. And then Escapade is hopefully launching soon, and we're going to talk a lot about that.
Yeah, let's talk all about that. Now, all of those others, the first one was a mapping mission, right? Was that a
Mars
mapping mission?
Surveyor was a mapping mission. It was fixed in local time, 2 a.m., 2 p.m. So the geologists would always have the same shadows on their rocks. They care about that. So, while that's great for geology, it's not great for upper atmosphere or atmosphere measurements, because imagine trying to understand the Earth's atmosphere if you could never measure it in the morning. That's tough, right?
That is a problem. Okay, and so all of those were single craft, right? And this one isn't. This one is a pair. You're literally, these are CubeSats. So you're doing this as an experiment. It occurred to me last night, you're literally rolling the dice. You've got a pair of cubes, she's rolling those laughing bones at Mars. So why are we using two? What's this going to do that's going to be different than what Maven does?
Right. That's a great question, because the instrumentation that Escapade carries, other than a pair of student-built cameras, which are kind of cool, but the main instrumentation that Escapade carries is no more sophisticated than what Maven carried. However, we have this stereo perspective, these dual point observations, and that's important primarily for two reasons. So the first thing is, two of the main limitations you have when you have a single spacecraft orbiting a planet and making measurements in situ. That's the key. Most of these important things we measure: magnetic fields, atmospheric escape rates. You need to be right there measuring it and sensing it, like sniffing it with the spacecraft. You can't see magnetic fields remotely. Well, except for there's certain places on the sun you can, but in general, you can't. You got to be there to measure it. So if you only have one spacecraft orbiting a planet, imagine it's going close to the planet, it's dipping into the atmosphere, it's going out into the solar wind to measure what the solar wind is doing, what the space weather environment is. You can only be in one place at one time. And so you can either measure the cause, which is the solar wind, or the effect close to the planet,
which is the magnetosphere on the planet.
With a delay of 2 hours, but the time scale upon which the physics is acting is 1 or 2 minutes across the whole planet. So
that won't cut it.
That won't cut it. But Maven has done a very good job. Maven, and also the European Mars Express mission too, I should add, together have done a very good job, although they have different instrumentation, a job of painting an average picture of what is a very dynamic environment. And that's definitely useful. There's a lot of phenomena that Maven has uncovered. Things like aurora, things like the shape of the magnetic fields twisted behind the planet, things like the atmospheric escape plumes, etc. All sorts of interesting plasma and upper atmospheric processes, but you can only be in one place at one time.
Sure.
The other really important thing you cannot do with only one orbiter is when you see something change in your data, you don't know whether you've just witnessed a global change or whether you've just entered a new region where the conditions are different. Those two things cannot be distinguished with one spacecraft. They can with two.
With two. And we're calling these satellites blue and gold. Why is that?
Those are the colors of UC Berkeley. That was the original thought. But actually, interestingly enough, they're also the colors of, I think, 4 other of our partner universities. It happens to be the colors of Embry-Riddle Aeronautical University, UCLA, West Virginia University. We have a co-investigator there. And okay, maybe it's only 3. Anyway, the point is that's why they're blue and gold. And our partners at Rocket Lab who build the spacecraft have nicknamed them Betty Blue and Goldilocks Gold.
Rocket Lab, the New Zealand corporation that is up and coming. I'd love to get a hold of them and have a talk with them, but we're not going to talk about the launch itself. That's another topic. Unless
they're building the spacecraft. Sorry, they're building the spacecraft. They're not launching
they're not building the launch. That's right.
Yes,
that's right. Oh, and you know what, folks? There is a magnificent discussion of them doing that on YouTube. I'll try and remember to put it in the comments later. Anyway, go ahead.
Oh yeah, they are in the spacecraft business as well as the launch business, and so they've been our main contractor to build the actual Escapade spacecraft buses themselves. And I should say, it's interesting. We started off the Escapade mission many years ago, and it was merely a concept, which NASA generously funded to the tune of $500,000 million for a 6-month study, which enabled it to really be fleshed out. They were CubeSats initially. They were really 12U CubeSats, but they've grown. They're more like fridges now. They're more like fridges, which is, still smaller than a classic interplanetary mission for sure. But they're now much larger than CubeSats, just because as their needs changed, there's a long history of how Escapade was originally manifested on one mission, on one launch, and then things changed with that launch. And the spacecraft has had to evolve over years, and it's now nearly 200 kilos each dry and 530 kilos each with fuel involved. So these are pretty big.
These have gotten big. These are okay. So these are no longer small, but they are part of the Simplex program. They're technically a Class D mission, which means that they're low priority because we already have Maven there. But these are going to add a lot of information. But they're high risk. They're high risk, and they were lower cost. So the reporting that I saw said that this was about 10% of the cost of a normal. So normal mission to Mars, about $80 million, which comparatively speaking is not a lot of cash.
Yes.
So this is worth it for them to do that. But how does that change how you design the craft? What does that do to the design? Because clearly you don't have nearly $1 billion.
No, that's right. Yeah. Okay. So first of all, before I jump into what we did, I think Simplex is an important experiment on the part of NASA in exploring the trade space between risk and cost. And I'll say this, that as a government agency, spending taxpayer money, there's an understandable need to guard and use that money well. And so this has led historically to a lot of conservatism within NASA's approach to missions. NASA will, gladly increase the budget significantly to go from I'm just going to make some numbers up now, but say a 95% chance of success to a 99% chance of success, even if you need to spend a lot more money to do that. And I get it, because failures, particularly with planetary missions, they're high profile. Failures are very embarrassing for the US government and for NASA. So NASA has been quite historically conservative. NASA hasn't had a deep space failure in 25 years. Which is
that's an astounding record.
It's an astounding record, and NASA should be, congratulated for that. But it's come at a price. It's expensive. Simplex is NASA's attempt to actually dip their toe into the water of seeing, well, wait a minute, what happens if we spend a lot less money? What success probability can we get for spending 1/10 of the money? Is it 50%? Is it 90%? It's not 10%, but it's not 99% either. So. No. It's somewhere in the middle, and this is an experiment to see where is that where does it sit? Where's that sweet spot? And does it therefore make sense to allocate a certain fraction of NASA's science portfolio to these higher risk missions where it's okay to fail once in a while?
Sure.
So
yeah, let's roll the dice. This is really genuinely, let's take a little chance and see if we can't get ahead.
Yeah.
You know.
So that's really the Simplex mission. So what has that meant for us?
Right. What does that do to how you design your spacecraft?
Right. Okay. So we had a bunch of trade-offs there. I think that
and you still have to deliver high impact science at the same time.
That's right. And, we had to do a few things. Certainly we had to go, and I should say that the cost cap that NASA initially set, excluding the cost of the launch, was $55 million in real year money. So we didn't get bumps up for inflation every year either. It was in 2019 dollars, basically. So one, we had to go with a relatively low cost spacecraft provider. Maven Maven spacecraft was manufactured, designed, and is now operated largely by Lockheed Martin, who have decades of experience in this field and who've been wonderful partners on Maven.
Very good at what they do.
But Lockheed Martin, Ball Aerospace, Northrop Grumman, all the big prime contractors, this cost cap was just too low for them. Because they're used to doing things a certain way. Now, I should say Lockheed has actually gotten into the small sat business too, and they're making the Trailblazer spacecraft and the Janus spacecraft. But what we wanted to do didn't match up with larger providers. And so we had to go with a lower cost provider. And so Rocket Lab really, really wants to get into this business, and they've been fantastic partners, but it's been inevitably with lower cost comes the use of common off-the-shelf parts. That's certainly something. There's a simpler propulsion system on board. For example, on much more expensive spacecraft, you can use the same fuel source to run the main engine as well as to run the attitude control thrusters that have little tiny amounts of impulse just to change the orientation. We've had to do them separately because that integrated system is say more expensive. That's one thing. Another big thing is less time, less manpower to do every single test we would love to do, because there's so many stages of the manufacture of the different subsystems, the instrumentation, the different parts of the spacecraft, where you want to test it as much as possible at every single stage before you do the various environmental testing, such as the vacuum testing, the thermal testing. We've had to be judicious in how we have allocated our manpower.
Yeah, so I imagine so.
There's been times when we would have wanted to do, 15 different tests. We can only do 8 of them, for example. And we think we've picked the 8 that are the most important. And sometimes NASA will say, well, why didn't you do the other 7? And we'll say, well, we didn't have the money. And so because, that's the deal. But it's new, and everyone's learning. Berkeley's learning, NASA's learning. This is not the common way of doing these missions. And so we've all had to just sort of take a breath and say, okay, we don't feel great about, skipping these tests, but we don't think we really need them, because anything that could go wrong that these tests would catch, our later tests will probably catch it too. So so it's okay. So yeah, there's a little bit higher risk that comes with that, less manpower and less time. There were some nice to haves that we just didn't have the money for either. For example, we would have loved to have put our main plasma analyzer out on a boom to give it a better field of view, so the spacecraft wasn't blocking a quarter of the sky. Maybe would have been only a tenth of the sky, but we couldn't afford that. The science would have been a little better with that. It's still perfectly adequate without it, but we also would have liked to have solar arrays that turn, so we would have more flexibility in the directions that we can point the different instruments while still getting solar power.
Still getting full power.
That was an extra $1 million. Couldn't afford that either.
Nope.
So these are examples. Also, we just couldn't afford to build a larger spacecraft. A larger spacecraft would have been able to have larger solar panels, which would have enabled a more powerful radio or a larger antenna. And so we've had to make do with it's a pretty small antenna, 60 centimeter antenna. The radio is, lower power than on a big spacecraft. So we have much lower data rates. And luckily, our data compresses really, really well. There's enough zeros in our data that it compresses nicely, and we are confident we'll be able to get all of our data down. But we were kind of lucky that it compressed as well as it did, because we ended up needing more than we thought, but then it compressed better than we thought, so it kind of worked out in the end. But it could not have. And other missions with imaging spectrometers or like really high res cameras wouldn't be able to get by with that. So that was something good too. And future Mars missions that are low cost will very likely need to use a relay network that's already there, like an infrastructure that's there. And NASA's certainly looking into that.
Yes.
And there was, for example, there was also one other issue. Rocket Lab went with a tank supplier for the fuel tanks, and there were issues with the fuel tanks. The company had problems, but Rocket Lab, to their credit, they've been, again, fantastic partners. They went and actually started an internal process to make their own fuel tanks. And they ran that in parallel once they started seeing things going wrong with this other tank supplier. And they invested a lot of their own money to now have the ability to build tanks in-house. That tank issue could have really been a mission killer, but like they really came through on that and fixed it. And so that was something that, had we had a much higher budget, that issue would never even have come up if we had a much higher budget. So anyway.
If you've seen Wild Space, a large portion of that documentary on, I think, HBO is dedicated to the story of Rocket Lab and how they did what they do. Mm-hmm. And you wouldn't have been able to do this thing 10 years ago. The technology wouldn't have been there, would it? No. So what kind of things have happened in the last 10 years that allow this to go on? What have we done? How are we getting better at this?
So some are technical and some are kind of programmatic. Let me start with those maybe. One is the advent of firm fixed price contracting. Historically, when the U.S. government wants to do something in space, they work with...
What firm fixed price contracting?
Yes, firm fixed price, meaning that, so this is one way of doing it, but the historical way of contracting has been called cost plus contracting, where the government takes on the risk of things going wrong.
Right.
And this is totally appropriate if you're like developing some brand new fighter jet or something where it's all such new technology that the company would never sign up to that much risk. They say, well, no, we're going to work for you. And then the company always gets a fee, some sort of a profit, whether it's 8% or 10% or something on top of the money they actually spend. But in recent years, starting in 2015, I want to say, with the commercial cargo, commercial crew programs for the space station, and increasingly contractors are doing it now too, where they say, this is the price, we will deliver for this price. If the scope changes, of course, if there's extra things they're asking us to do, then of course, add the money. But we will eat any cost problems ourselves, and we will only charge the government a fixed price. That's been a big part of why Escapade was possible, because Rocket Lab said, this is our cost, and that enabled NASA to not have to worry about potential cost overruns on the spacecraft side. So that's certainly one thing that's become much more common recently. Boeing and SpaceX are doing it for the crew.
Boeing is trying.
That's a whole different conversation.
Well, you can see the change literally happening with Boeing and them trying to come across from a cost plus to a fixed price.
That's right. And some companies are having difficulties with that for sure. Whereas, SpaceX has been largely a fixed price provider from the beginning. And Rocket Lab is, as far as I know, Rocket Lab is only a fixed price provider. I don't think Rocket Lab does anything.
I couldn't speak to that. But so that's one of the things that's made this possible, is that we've seen this paradigm shift in how we pay for these things.
Right. There's a few other things that are maybe a bit more pedestrian, but still quite relevant. One is because of Maven and because of the Emirates Mars mission too, because there's team members that have worked on both of those things. We have a lot of experience with the Mars environment. We really know the kind of gotchas that can get you in Mars orbit, whether it's constraints on whether, when Mars shadows the spacecraft and so it doesn't get power for, 45 minutes or something like that. Even things like the erosion environment in the upper atmosphere of Mars. There's a lot of atomic oxygen up there. And atomic oxygen is highly corrosive to certain surfaces within instrumentation, certain things on spacecraft. That's a lesson we learned the hard way on Maven. We used a coating on Maven that wasn't ideal. So we've, used a better coating, which we know is going to survive that environment. So there's just lessons learned like that. And just all the things we're measuring, the magnetic fields, the plasma environments, we knew exactly how to build our instruments because we know what we're measuring. We're just measuring it from multiple perspectives. So that was important too. Another thing is our instrumentation. Our instrumentation is either very simple or very high heritage, meaning we've built multiple copies of very similar things before. And so there's less risk in terms of the development process. So our magnetometers—
You know what you are doing at this point.
Right. The same team that built the Maven magnetometers at NASA's Goddard Space Flight Center built our magnetometers. They're a little different design, but it's a very similar system. Our thermal plasma sensors come from Embry-Riddle University. They've flown on the space station on sounding rockets. They're built by students. They came in also very low cost. Our main plasma analyzer, it's not a simple instrument. It's quite complex, but it's a very, very near copy of what we built for Parker Solar Probe. And what we're also building for the Lunar Gateway space station as well, and for other projects too. Like it's an instrument that we know how to build. So that's ways of keeping the cost down. There's not a lot of money for significant science preparation work. There's a lot of ways we just had to cut things down to the bare minimum. But to answer your question, technically, things like solar arrays have gotten much more reliable and much more efficient.
The efficiency's way up there.
Right. There's a lot of, spacecraft, say flight computer, off the shelf, much lower cost components that are much more reliable than they used to be before. Before it had to be like military spec for everything. Now it's, you can buy these things at a much more reasonable price and they'll still work.
Yeah. And you know what? I'm noticing you have a lot of partners who are really engaged in this mission. This seems to be exciting. People seem to be. We had Jonathan McDowell from Harvard Smithsonian Center for Astrophysics. He's a space historian. And I was, talking about what we've got coming up next, which reminds me, I believe it's next Monday. We're going to have Eric Berger from Ars Technica in, and we're going to be talking about his new book on SpaceX, and it's called Liftoff. Excellent read. I'm in the middle of it right now. I'm savoring it. It's a great read. Anyway, so Jonathan, to bring that back, I mentioned that you were going to be here, and he was very excited. That's an important mission, he tells me, and this is a guy who really knows. He's been tracking satellites and space launches since 1989. So he was excited. You seem excited. I'm excited. Everybody's excited.
I'm glad.
This is an exciting mission. So it's unique, isn't it?
Yes, it is.
And why are people so excited? Why are we so excited?
So I think partly it's the stuff that we just talked about. It potentially being a pathfinder about how missions can be done for much lower cost. And if it turns out that we can spend 1/10 of the money and still get 90% reliability, or even 80, in terms of science per dollar, that's way better than
it's 10 missions for one.
Yeah, right. Exactly. And it's okay if 2 of them fail, let's say, right? Because that's
great.
You're playing the odds. So I think that's one reason why people are really, really excited about this. But the people who are sort of more into the science of it, I think they're seeing the science of heliophysics, which has been mostly an Earth-centered, an Earth environment-centered endeavor, expanding to the other planets. So let me bring you back to the late 1980s.
Please.
So the state of understanding of the Earth's magnetosphere, the processes that drive, space weather, the hazards of space weather, things that drive the aurora, etc. It was sort of where we are with Mars now, in the sense that we had a pretty good average picture of the stuff that happens, but we hadn't really connected the causes and the effects yet. And that was when we first started doing multiple spacecraft missions, because we realized we needed to be in 2 places or 3 places or even 5 places at once to simultaneously measure the plasma environment, the space weather environment in one place to understand the effect of the conditions in one place on conditions in another place, because the plasma moves so fast, so much faster than the spacecraft can, that you need that multiple vantage point. And so we're excited to be doing that for Mars for the first time. And I think, there's a I think, hopefully this succeeds and it shows what can be done at other planets. And that's important for two reasons. One, part of the reason we do this on Earth is just that it's purely an interesting scientific laboratory. It's plasma physics in a given laboratory, which is our magnetosphere, our global magnetic field, and how that interacts with the solar wind. But every planet is different, and Mars has this hybrid magnetosphere, which is this mixture of an induced magnetosphere, meaning that there's currents which flow in the ionosphere that produce a magnetic field. But also Mars has this really unique crustal set of magnetic fields. So, Earth's global magnetic field is rooted in its core. It's motions of conducting metal in our core, mostly iron and nickel. And those motions produce a magnetic field. Mars doesn't have that. It's
essentially a generator.
It's a generator. It's called a dynamo. Exactly. Mars used to have one of those a long time ago, but it lost it. But the presence of that field, as the rocks on Mars, in the presence of volcanic activity and impact craters being formed, when those rocks cooled, they took on the magnetization of that magnetic field. But Mars had huge volumes of highly magnetized crust that resulted from this process, and those are still there today. And so as Mars rotates, it shows a very different magnetic face to the sun, because one side of the planet is much more magnetic than the other side. This is true it's true north-south, and it's true east-west as well. And so that means that as Mars rotates, these crustal magnetic fields are connecting and reconnecting with the draped interplanetary magnetic field, and that produces magnetic reconnection, acceleration, aurora, and we're only scratching the surface of that stuff so far.
And so that's what we're going to be looking at with Escapade. I can't ask you what you hope to find, but you might have some idea. I mean, since you're so experienced with Mars, what have you found so far? What are we looking at? How did Mars lose its atmosphere? Where did water go? And all these questions are tied into the atmosphere and the magnetosphere, are they not?
They are indeed.
So what have you learned? Tell us about what your research has taught us about Mars, about what could be our next planet.
Right. Well, okay. So I guess the big picture stuff and the main motivation to send Maven, and ultimately Escapade as well, is to understand, where did the water go? Where did the CO2 go? Mars used to have stable, at least episodically stable, liquid water on the surface. There's evidence for rivers and lakes and potentially oceans in the past. Yeah. And we know the conditions were warm enough with a thick enough atmosphere to maintain this environment for, perhaps not the entirety of the early history, but certainly long stretches of millions of years at a time.
Millions? Okay.
Millions of years at a time. And then that atmosphere, 90-something% of it disappeared. And understanding why is a major part of why Maven was sent, and ultimately Escapade is sent. Because as I said, Maven has enabled us to say, well, we know that when the solar wind is in this range of density or speed, that we get atmospheric escape rates that are in this sort of range, but we've never been able to do the cause and effect at the same time, to say, what happens when you get a big pressure pulse from the solar wind, a big interplanetary shock hitting the planet? What happens to the atmospheric escape rate at that time? Maven can tell you, on average, they can say, well, we can either measure the shock or we can measure the escape. We can't measure both at the same time. Escapade is going to do those things at the same time, unraveling that chain of cause and effect. That's something I'm really looking forward to doing. And I'm also looking forward, just even when the solar wind is relatively stable, any planetary atmosphere, upper atmosphere and lower atmosphere, has wave activity and ionospheric disturbances in it. And these things happen on the order of minutes. We know this on Earth because we've been studying it for years and years and years with all sorts of
Right.
ground radars, etc. On Mars, we have no idea about this behavior, none at all, because we've had to wait 4.5 hours every time we've had Maven. So okay, you come in, measure it, and then you got to wait 4.5 hours to measure it again, and you don't know how it's actually changing on the timescales that it's mostly changing on.
So now you're going to get some contiguous data points that are going to allow you to see the process in motion as it occurs, essentially, right?
Exactly.
And what is that going to tell us about Earth? We're not going to get our atmosphere and liquid oceans blown away, I hope.
No, we're not. We're not.
No, we're not. Oh, phew. That's a load off. I was going to be awake tonight worrying about that. But what does that tell us about our planet? What does it tell us about Venus? What does it tell us about the rest of the solar system? And in the future, what can it tell us about exoplanets as we find more and more of those and get better looks at them?
That's right. Well, I think, whenever you have a field like ours, which is, there's like 3 different kinds of investigation of things. I would say there's theoretical, which is one. Then there's experimental, which is where you can finally control the parameters of your experiment in your lab. And then there's observational, where it's an experiment, but you can't control you can't turn the knobs. And so that's what, pretty much all of geophysics is, and certainly space plasma physics is. Mm-hmm. And so when you look at what happens, for example, in the near Earth environment, you only have one set of knobs, and they're fixed in certain places because we have a certain gravity, we have a certain strength of a global magnetic field. And so we can observe and understand the behavior of the plasma, but only in that particular environment and only under the conditions that appear there. When we go to somewhere like Venus, there's a stronger solar wind there. There's similar gravity to Earth, but there's no global magnetic field. And there's actually a much cooler upper atmosphere at Venus than there is at Earth. So there's actually a very different environment. So yeah, it's
that surprises me. But yeah,
it's because Mars and Venus both have CO2 as their primary atmospheric constituent, and CO2, because it's a 3-atom molecule, it has a lot of ways of vibrating and losing heat. And so the CO2 in Venus's upper atmosphere gets cool really fast. So even though it's incredibly hot on the surface, the upper atmosphere of Venus is quite cold, similar to Mars. Unlike on Earth, where it's mainly oxygen and nitrogen, where it's actually quite warm. So there's different planetary conditions that exist at every planet. And as I said, Mars doesn't have a global magnetic field, but it has these very strong crustal magnetic fields. And so it's a different plasma environment. And to your question, exoplanets are going to be their own ball of wax. They're going to run that gamut too. Some are going to be rotating faster, slower. Some are going to have global magnetic fields. Some won't. Some will have warmer atmospheres, cooler atmospheres. So it's a plethora of different planetary environments. And to understand plasma physics better in general, you want to measure these things at multiple environments.
This has got to be exciting for you. You've got to. I mean, you're revealing a set of paradigms that we're going to be able to use well into the future. This is groundbreaking stuff as we, expand off of the Earth. We're going to need this information.
That's a very good point, Dave, because one of the other major reason, other than scientific interest, that the heliophysics division at NASA even exists, is to understand the space weather environment on Earth, to better understand the hazards it poses to astronauts, to our power grids on Earth, to the health of our satellites, to our whole civilization. We need to understand what those threats are. To even, for example, GPS doesn't work unless you have a really good model of the ionosphere, because the ionosphere disturbs those signals, and the
delay will throw off your position.
Exactly. And so if we want to have global navigation and positioning on Mars, we're going to need to understand the Mars ionosphere, which is very different from the Earth's ionosphere. If we want to have long-range surface-to-surface communication where you can bounce radio signals off the ionosphere on Mars, because maybe the satellites,
which is how we do it on Earth.
Exactly. We're going to need to understand that better for that reason too, and the radiation environment as well on Mars, because Mars is much more exposed to hazardous space radiation than Earth is.
Okay, folks. Now you just heard Rob explain why you need to be here on Friday at it'll be 12:15 Central Time PM. for our weekly sun talk with Debbie Bird and C. Alex Young, who is a heliophysicist at NASA Goddard Space Flight Center. He studies the stuff Rob is talking about all day long, and he contributes here. We have a daily sun news. We put it out every single day except whatever day it is we don't publish. Sorry about this, Monday we don't publish. And so anyway, we have a trio of excellent sun experts, including Alex and Raul and Armando. So check that out. Go subscribe at earthsky.org, and that'll be Friday if you want to get into your sun. We are running up against your time limit here, Rob. I understand you have places to be and things to do. You're a busy guy.
There's a lot going on right now as we replan our launch. Briefly,
right, you got knocked back.
Yeah, we were supposed to launch this October, but a decision was made by NASA to postpone the launch until sometime next year. We're still working out our alternative trajectories. The earliest opportunities are in spring 2025. There's others in fall 2025, etc. So we are frantically, well, not frantically, it makes it sound like we are enthusiastically exploring other options. Ourselves, Rocket Lab, and the launch provider Blue Origin are working closely together to identify new launch opportunities for Escapade.
Well, thankfully, Mars isn't going anywhere anytime soon, so we'll get there eventually, Rob. Thank you so much for joining us. Folks, like, subscribe, visit earthsky.org, sign up for the newsletter, get all the latest. We're there every day of the week but Monday. We'd love to have you join us. Anyway, Rob, thank you again. And folks, we will talk to you next week, same bat time, same bat channel. Bye-bye.